So what is a sensor? Well, a sensor is something that detects or measures a like an input, like a proxy sensor detects like if something comes within proximity of itself, and then it records or indicates, and then it sends an output. So why should we use sensors? So we can use sensors as feedback for robot parts. Like if we need to zero an elevator, we can use a Hall effecting, and that can sort of help set zero with your elevator. And we can use it for motion control. So like gyro sensors, we can use those for like detecting what angle your robot's at and when it's driving. And we can use detecting field elements. So we can use like cameras to detect vision elements.
So when choosing a sensor, there's a lot of things to consider. This includes what kind of sensor output, signal output you want, what you're actually using it for. You don't need to get a sensor that does a ton of fancy things if you're only using it for one specific thing. Certain things like accuracy and precision, and then also the electrical requirements, voltage and current, what your robot can actually provide for your sensor. So some examples of sensors are the limit switch, and this is just, it can detect if it is pressed, and that closes the circuit and sends that back to your RoboRIO. There's also the Hall effect, which can in many cases be used as a limit switch. It detects magnetic fields, and so in that case you can place a magnet on a place, and then when it moves by you can detect that.
So another example of a sensor is an encoder. So it measures rotary motion, and it can measure RPMs. Usually you can use these for like elevators or drivetrains, more commonly with drivetrains. And there's two types. So right here you can see a mag encoder, and those use magnets with small electromagnetic sensors that detect the polarity of the magnet. And then also there are potentiometers. So potentiometers are they're analog, but they're really good for like measuring certain angles. So say you've got a wrist on your robot, and it has to be at like a certain angle if you want to score a game element. You're going to want to use a potentiometer.
So there's also gyroscopes, which measure the angle, and accelerometers, which measure acceleration, and that's often used to detect your tilt. So that in that case, it'd be measuring the acceleration due to gravity, and it's actually included in the RoboRIO, but that's not super accurate. So you may want to find an outside one. There's also proximity and beam break, and these are used to detect if like how far away an object is, or if there's an object within a certain area.
So these are some sensor boards. So these are two examples of a sensor board. There's the FRC gyro and the Pigeon IMU. So they're both gyroscopes, and like Rachel said before, if you want to upgrade your RoboRIO's gyroscopic abilities, then you're going to want to get one of these. And so, next slide. So the Pigeon IMU, as you saw on that previous slide, has a ribbon cable plugging into the Talon SRX data port. And so the Pigeon IMU uses ribbon cable to connect to, it doesn't matter really which Talon, but it doesn't connect to the RoboRIO like other expansion boards like the NavX. It doesn't use the expansion port.
So when putting your sensor on your robot, there's a lot of things to consider in the mounting where you put it. So you want it to be in a protected area so that it's not going to get affected by any like bumping from other robots. It's not going to have things fall onto it. The sensor has to be able to see or be able to actually do its purpose. So don't put like a beam break sensor and have something in between the two, the emitter and the receiver. It has to be secure. So if it moves around, then you're not going to get accurate data. And the wires should be having a connector, not solder, so you can actually change it out if you need to replace it. Also, make sure there's no magnetic or electric noise which can interfere with it. So that would come from a motor or from high current wires. So you can use Faraday cages to help with the electric noise, but that does not help with the magnetic. So make sure that you place it away from a motor. And then, so here are different graphs of different types of signal outputs. So there's DIO, which is digital input output, which is easy to use, super simple and useful. And then there's analog, which has values between a whole range of values, and it is more susceptible to noise, but so it can be not as precise. There's also digital serial, which is precise and high resolution, but but it's more complex to use.
So here you can see the RoboRIO. We go through the ports. So you've got the CAN port up there, I2C. We'll talk about that later. RS232. I don't think we talk about that in this presentation. Then you've got digital input/output ports. You've got your RSL relays. You've got analog inputs, and you've got PWM, SPI here, Ethernet, 2 USBs for stuff you want to use in your robot, like USB cameras, and then USB-A for connecting to computers, and then you've got your power input. So with RoboRIOs, they're good from 7 to 16 volts. As long as you keep it within that range, you're not going to be browning out. But when it goes like below that, you're going to start browning out. And so here are the stages of browning out. So 6.3 to 6.8 volts. The 6 volt rail starts to drop. And so then once you get down to the 4.5 and 6.3 volts, that's when things start to get a little hairy. Everything starts to like shut down. It's sort of in like survival mode, I guess you could call it. And then once you're at less than 4.5 volts, everything just stops working. So this is really important when you're like thinking about motors and mechanisms. If you have something that uses a lot of current and a lot of voltage, I don't know, try and find something that uses less voltage.
So on your RoboRIO, in the top right corner, there's a bunch of status lights, and next to them is labeled what each one is showing you. And so here's a table of the different lights, the different states that they're in that show you what that actually means. And you can find this in the user manual. You don't actually have to memorize it, but it's a good thing to have handy so that you can access it really quickly when diagnosing issues.
We'll do questions at the end. So, yeah. So the CAN bus is the controller area network. And so in the CAN bus, you have the CPU and you have nodes, and then they're all connected by a bus. And so with each node, it has a microcontroller, a CAN controller, and a CAN transceiver. And so CAN transceivers are used to receive and send signal. The CAN controller sort of converts all of the CAN data to information that the speed controller can actually use, or the node can use. And then the microcontroller is what performs all the processes. And so with CAN, everything is really just daisy chained together. And so what that means is, like, you've got one thing which connects to the next thing, which connects to the next node, and then that node connects to another node, and then it connects to the next node. It's not like everything is connected to one central CPU. So if we go to the next slide, you can see, yeah. So without CAN, you've got that, and it's kind of a mess. It can be really difficult to work with at times when on your robot, because if you've got like a lot of speed controllers in one area, it's going to be really hard to trace wires. But then with CAN, you get something like this. And then this is an example of daisy chaining with speed controllers, and each speed controller is a node. And so CAN, the 3 main CAN components that you need on your robot are the RoboRIO, the PCM, and the PDP. And so with the PDP, you've got the terminating resistor, which is technically the 4th but not really spoken about important part of the CAN loop. And with the terminating resistor, it's sort of, well, it's required to reduce signal reflection back through the CAN loop, which can mess with signal. And so when you're daisy chaining all of the CAN components, the nodes can just go anywhere along this circuit. It doesn't matter where. All right, and so this is the CANifier. It's a really useful CAN component, because what you can do is you can convert digital input/output sensors to CAN. And so it allows you to use sensors in the CAN loop without having to run it. Like if it's really far away from your RoboRIO, you don't have to run a cable all the way back down to your RoboRIO. Instead, you can just run a short little cable to your CANifier and then convert that to the CAN loop. It also helps with wiring. Yeah, usually when you have a CANifier, what you're going to want to do is have this be at the end of your CAN loop and have a terminating resistor on the CAN port. And then that means with the PDP, you're going to have to change the little connector to the off position for the terminating resistor. So I2C, not that many people use it. I don't know any that do actually, but it's really useful to know. It's a simple protocol to talk to sensors. It uses a master CPU and then 3 slaves, and you don't really need to know like how much it does, or you just really need to know what it does. uses 3.3 volts, and it's kind of like the CAN loop, but that's really not all that you need to know about it.
So DIO is a control type, and it has 3 wires. It has power, voltage, or power signal and ground. And so this is used for sensors that have either 3.3 volts or 5 volt output. So it's just ones or zeros basically. And it is used to connect to the RoboRIO. And then there's PWM with this pulse width modulation, and it has different cycles, full and no power. And so this can be used. It's called the duty cycle, is the percent of time that it's at full power. So that can be used to simulate an analog output. And so if you have, like, for example, a motor and you give it half of the time it's going to be at full power, then that's as if you're giving it half power the whole time.
All right, so SPI, we talked about this a little bit earlier. It's another example of slave master control systems. Here you can see the pinout for it, and it uses 5 volts and 3.3 volts. It's sort of similar to the ribbon cable that you use on the Talon SRX. But again, it uses, it can output 8 to 12 or 16 bits for the other slaves. And so here's an example of wiring with the SPI. Okay, so relays. You can use relays to take a small current and run that through an electromagnet, which then allows a flow for a larger current. So, so you've got a mechanism that uses a lot of voltage, but you want to trigger it with a really small amount of voltage. You'd want to use a relay, and so it has 5 volt input, and it's really useful for spikes, Vex robotics, H-bridge relays from Vex robotics, and also for motor control.
So on the RoboRIO, there's a port in, like, the center kind of lower half, and this is an expansion port. So you can use it to plug in other boards if you don't have room, because sometimes you have a lot of sensors and you want to be able to plug all of them in, and you don't have space on the RoboRIO. So then you would add on a expansion board. And so there's different ones. There's already pre-made ones out there that you can buy. They have different ports that they expand. You can also make your own, but ones that have active ports have to be pre-approved by first. So these ones are already approved, and so they're a good to pick from.
So here you can see all the other ports that we didn't cover. Input, it's just coming straight from the PDP. Red goes in B, black goes in C. And then you've got your USB device port, so when you want to connect to your computer and control it directly. Here's your Ethernet port for communicating with your radio. And then you've got USB host ports, which I said earlier were for USB cameras. And then here's the RSL. So we have a lot of people, so I'm going to assume there are a lot of questions. So yeah, start asking. You back there?
Why do daughter boards have to be approved by first if they have active components on? Why is it not just fine if it doesn't control the outputs?
I guess they just want to, like, regulate what is actually being allowed to be used, because they don't want just anything to be allowed. Like, you want your circuit to not have, like, a ton of special things that they can do that other teams can't.
So, like, would it be mostly just like having like a board that's communicating with something that's like if the board was communicating with like something that's outside of the competition?
I don't think it's necessarily that. I think first is just trying to keep an even playing field for everyone. So there are like there's certain boards that do certain things using specific code, but then there's other boards that do the same thing but with different code. I think it's just like programmers have different preferences, but also there are some boards that are better. Like they're not all the same.
And if you want to make your own, you can. If it doesn't have an active device on it, then that's perfectly fine. And you can get it approved, but that is a whole nother process.
you down there.
How often is traffic on campus?
So it really depends on how many components you're using. If you're like, I don't know, using all of your canned components, if you're using all, like, I'd say around 16 or 15 nodes is when it starts getting a little bit cluttered. Yeah, so try and keep it around like 12 to 13, which I think was what we found was working the best.
Two questions. One, how often have you guys used an expansion board? Have you ever needed it?
Yeah, so this year we used Pigeon IMUs, and we right now we're working on an off-season robot that's using a NavX, and I think in 2018, like 2016 through 2018, we used Spartan boards, and we use the Spartan boards for all of our PWM signals and also gyro, but we just used the Pigeon for gyro this year.
I'm pretty sure we've used an expansion board every year since 2014.
So it's like WB. So if you turn the PDB resistor off, it's just another node in the CAN bus.
Yeah.
Okay.
Yeah.
You mentioned the Spartan. What's a Spartan board?
So a Spartan board is something made by West Coast Products, and it doesn't just cover the expansion port. Actually, it covers all of the ports on the RoboRIO, and so it's a way of like taking the expansion port and sort of integrating more digital input-output ports in, more PWM pins in, and it's also a gyro sensor. So I think we have a link to that on the expansion board slide. Yeah.
No, it was designed by Team
Oh.
971, the Spartans
Okay.
from Mountain View. And
Oh,
all
well.
of their
That's
current
fine.
mentors, former team members, Austin and Travis Shue, designed the board and had it built. And to share it with the community, they worked with West Coast Products to make it generally available. It was a great way to deal with problems of getting WPM connected. Now that most of the motor controllers are CAN-based, it's less essential. It also helps protect your RoboRIO from bits of aluminum falling in it, which I think is very handy to start.
Any other questions?
Can we get access to this slideshow?
Yeah, so it should show up on our website in a little bit. It'll be like a video of it, so I don't think it's actually the like slideshow itself. Yeah.
Yeah, that's the one.
Anything else? Anything about the team in general?
Can you guys go more into like actual applications, examples of the sensors used?
Yeah. Do you want to go back to the slides of the examples? Okay. There's one more before it. Yeah. do you wanna explain it?
So with a limit switch, it can sort of be used as like physical analogs or physical proximity sensor. So if you have to like zero a mechanism or something, like a wrist, if it comes down all the way and then touches the limit switch and presses that down, you can use that for zeroing. It can also be used for detecting field elements. Like, honestly, I would say using a proximity sensor for detecting field elements would be better, because that can have like a little bit of a gap, but with a limit switch, I feel like it would take a lot of beating. But for like robot parts, I feel like it's pretty good. Hall effects are similar to limit switches, but they use a magnet and an electromagnetic sensor on the board, and it detects when the magnet enters. The electromagnetic sensor detects when the magnetic field comes close enough with the sensor.
So like we use this on our elevator for the positioning. So we had the magnet at a certain height, and then the magnet on the elevator, and then the sensor on a certain height. So then you know when it reaches that height.
So is that just for your limits, or was that for your zeroing also?
That can also be used for zeroing, yeah.
What's the error in the position?
I would say like half a centimeter. So it detects it like when it comes within half a centimeter of it. So I don't like yeah, that's when it can detect it. I don't really think it has much error, but yeah. All right, next slide. Okay, so with encoders, you don't have to use it necessarily for a drivetrain. You can use it for like an elevator, measuring how fast your elevator rises can be useful in certain situations. There's also not just magnetic encoders. There are physical encoders, which usually have like a 5-pin output, but you don't need all 5, you just need 4. One of them's a extra signal pin. And they do the same thing, but the good thing about having a magnetic encoder is that you don't need like a physical connection, because with a physical encoder, you have to attach a shaft to another. You have to attach the shaft of the encoder to another shaft that's like on your drivetrain, and that's just another part that could fail. But with magnets, your magnet's not going to come sliding out if you super glue it in place. And then with potentiometers, I think I covered that already. It's really good for angles and rotational position. There isn't much like slop in a potentiometer, like if you've ever felt one. They're pretty solid. I have never had a problem with a potentiometer. Yeah.
How accurate a position do you get from the RoboRIO's internal ADC?
I don't exactly know. I know it could be better, which is why we use expansion boards. I would say probably like 5 or 10 degrees ish. And then, did you have another question or no?
Do you know of any expansion boards that have dedicated ADCs on them? Because I know.
Wait, by ADC do you mean gyro or something else?
Analog to digital converter.
Oh, okay. I don't know exactly. I don't know. I'm really familiar with the Spartan boards and our Pigeon IMUs. I have never encountered one of those. I think the NavX might. Do you know?
I don't know.
No? Okay. Yeah, I'm sorry. Anyone else? No?
What application is that for? Just out of curiosity.
Well, I mean, if you're using a potentiometer at all, you need to know a really precise.
Yeah.
I've known in my dabbling in using potentiometers and built-in ADCs and stuff like that, the reading you get tends to jump around a bit, like by 1 or 2 counts. Just if you read it and then read it again, it'll be off from the last one, even if you haven't moved. So you can't rely on it too much.
Yeah. I mean, you can also use. Encoders aren't like only just for measuring like speed and rotation of rotation. They can also be partially used for angles. I think we usually use encoders for angles, right?
I think so, yeah.
Yeah. So, I mean, if potentiometers aren't exactly your cup of tea, you can also use encoders. All right. I think I saw a question over here earlier.
Do you guys use the contact sensors at all, or CTRE?
I don't think so, no. All right. Any last questions before we finish up? Well, all right.
Cool. Thank you all for coming.
Yeah, thank you.